So hello everyone. My name is kind of a nightmare to pronounce, so I'm gonna inflict that on you only like twice. I'm Michał Woźniczak, and this is going to be about how taking some cues from a different programming paradigm can like way improve whatever code you've got, and on a specific case study. So you know how in sometimes in TV shows it starts with a completely seemingly unrelated scene, and then you don't get what the deal with it is until later, and you're like, oh, that's what it was for. So let me tell you about a book I bought a decade and a half ago, and it's called Programming Erlang by Joe Armstrong. I think it's in the second edition right now. So basically, I don't think I've written a single production-worthy line of code in Erlang, but if you were to ask me what my most influential book I've ever read on programming was, I'd say this. Basically, Erlang is kind of a quirky language, and I don't mean in terms of syntax, because that's a thing of its own, but in terms of there's a lot of language constructs that are basically baked into the language that at first glance are kind of incomprehensible, and you're like, why would they put, oh, wow, okay. And I'm going to start with an easy one, and that's going to be pretty familiar to everyone who's ever written Python, but that's the first where I saw it in. So if you've written Python, you might recognize that this is pretty much a list comprehension, and this is the first example of a programming language where I've seen it. And if you're not familiar with Python, it basically takes a list, tells you how to modify this list, and it tells you how to modify this list, and a really like visually immediate way, basically. So other things take a moment to understand. Like for example, in Erlang, you've got a dedicated construct that you give it a list, and it automatically splits the first element and then the rest of the list. So basically, it takes element at index 0 and then the rest of it. And you might be like, why make this a construct? Why make this particularly optimized for this given language, right? So, but then we get to the functions that can be defined multiple times, and there's this cool thing called pattern matching, which basically you can define a function multiple times, and Erlang will basically figure out which case applies here, and then use the appropriate definition. So basically, the thing about Erlang and what sold me on the concept is that it's meant to be like optimized for parallelized processing, basically out of the box. And they basically tell you that you can run this on multiple machines, and it's going to execute everything you throw at it concurrently and basically seamlessly. And in this case, this works like you give it a list, and it does the MasterChef thing where it chops it, uses the appropriate function, chop, 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 and first it does like the heads and tails thing and the number, calls the appropriate one, and then because this is a functional language, it's all recursion based, right? So it's a really concise way to slice things up and delegate them to multiple workers that can be working across multiple processes, multiple machines, and so on. But there are some things that, for me at least, took a while to get used to. Like, for example, we start with a typical variable assignment. We assign the value 3 to variable A. And OK, it tells us, yeah, it's 3. And then we try to reassign it, and then it basically craps out. It will not let you reassign a variable because, and this is kind of shared across multiple functional languages, that concept of immutability. That's once you've got a variable, it does not change. And at first glance, why would you want this? They are literally called variables. And this doesn't vary from instance to instance. And you actually To change the value, you have to use to call the function again and with the new parameters and so on and so forth. So at first glance, it sounds completely insane. But let me maybe start countering that argument with what I think is either a staple of Python entry interviews or damn well should be. Because at first glance, this looks pretty safe. So you've got a function, give it a bunch of arguments, and then you've got an optional argument that if you supply it, it will add those arguments to the list. And if you don't, it just uses an empty list, right? Simple, straightforward. It adds the output, adds the arguments to the outputs, returns the outputs. Simple enough. So let's give it give it a go. So at first glance, that's what is advertised. We didn't supply the output, so it worked on an empty list, added 1, 2, and 3 to that list. 1, 2, 3, nice. So let's, oh no, right? Because there's a quirk in Python when you declare a function, basically the variables in here are assigned ones. And it basically refers to this same element. And because a list is mutable, because it can change, well, it does. So that's kind of a first case for immutability, that if this list was immutable, it would either transparently create, because notice it doesn't do this when you give it a string as a default value. It doesn't do that if you give it a number or a tuple or whatever that's immutable, because at this point it knows it should create a new fresh instance just for this function alone. You can abuse mutability in other aspects. For example, here's a monstrosity I found on Twitter a while back. And nice thing, it also translates well to JavaScript, in which you can copy a dictionary or a object if you're a JavaScript guy. Or a person, you basically iterate over items and you do nothing seemingly, but that dictionary gets copied in a most obnoxious, unintuitive way because dictionaries are immutable. But yeah, we're actually here to see some real life examples. And I say that with quotation marks because I can't show you the actual code. I can just show you the idealized version of it because I just can't. But hopefully this is kind of a double-edged sword, but in reverse, because maybe by making the example slightly more generic, I can get some gears turning, and maybe you will spot some place where this might apply to your project. So basically the setup is this. We've got a function called process elements, and basically it's a beast. It takes, on a good day, it takes minutes to complete, possibly more. And it takes a bunch of elements, and what it does is it returns the elements that went through the whole thing without crashing or without breaking. So if something breaks, we just remove it from the list of elements, and then we return whatever's left. So what can possibly go wrong, right? So let's start with the problems. Here's a less idealized version of the process elements. It goes a little like this. First, we've got kind of a eligibility check, which basically removes elements that are not to be processed for whatever reason. They don't match the criteria for processing. They are not ripe yet. So we remove them, and if we ended up with an empty list, we just return an empty list. And we've got a bunch of functions. Like, for example, we've got functions that maybe are called on elements. Maybe we've got functions that are called on distinct bits from an element. Maybe, for example, we use some external libraries because, like I said, the function itself is huge, but someone had at least the good sense to put some of it in separate modules that serve a specific function. So yeah, so maybe it does that for an element, maybe it does for multiple elements, who knows? So here's first problem. For example, the list, sometimes when something fails, the element will be just popped off a list, which in a serialized processing, fair enough. It just removes the element, because I should probably say the element is, when I say element, I mean like an identifier of an element. So it's a really lightweight thing. Or for example, here's a really intriguing thing that I found, where if instead of popping an element, it would use the index of the element, sorry, the slice of index and index plus 1 and make that a list. I did not know you could do that. And honestly, nobody should know that you could do that. And you should immediately forgot you saw that slide. And sincerely, I encourage you to do so. And that's only when you do a thing within the module, because you can also, let's say in a separate library or a module, you can do that. But if it fails, it just pops the element. And I think based on the previous slide, you can kind of see where I'm going with this. I'm gonna fix that in post. So you can't really speed up things with parallelization, because the list keeps changing. And specifically, if you do that trick, the index will have changed if something modifies it in a really weird race condition. And again, do not do this. And for example, we could also might want to know what the status of the elements table is. But several functions are basically playing keep away with it, because we are giving the functions as a parameter the elements list. And remember, it's mutable. So if a function within a module within a module within a library modifies that elements table, it's modified everywhere because they are passed by reference. So, and also kind of a side note, it turns out that giving just the list of items that have went through the whole process is not really sufficient when you want to enable like a more robust logging. This is not directly tied to the problems above, but you know, small details like that really help you sell the thing, right? Because on top of being able to speed things up, you will be also able to provide more robust reporting for your Kibanas, your Humios, your whatever you have rolled for in terms of like dashboards and logging and reporting and so on. And we all know how management loves reporting and dashboards. So all the more reason to have a closer look at what's going on. So let's see what we can do about this. When we look at the process elements function again, we can see, first of all, two sides to this coin. First, we've got what I've called a discriminator, which basically discriminates, removes all the elements that are not to be processed for whatever reason, and this basically short circuits. And then we've got functions, obviously with much simplified names than previously, that do processing. And it turns out, when we did a discussion, it doesn't really matter what order those functions are called in, just as long as, I mean, turns out partial processing is fine as long as the element was processable. So it was not removed by the discrimination process. So let me talk about a processing status object, which is basically the cornerstone of the logging thing, first and foremost, but not only. We've got three attributes. First is processables, which is basically the materials that did not, elements that did not fail yet. And then we've got failures of two different types: transient failures and permanent failures. Transients are essentially like, for example, an API wasn't responding, or we've got an unexpected exception. Basically, something that if we rerun the processing on this element, it should probably get reprocessed properly the second time around. And permanent failures, in our case, indicated a data error, which as developers we loved, because that means it was basically the data guy's fault. So not on us. And then we've got functions that may mark an item as failed transiently or permanently. And then we've got a freeze function, because when we are still processing something within a scope of a function, because I should say we want all of those functions to each return a processing status object. But while we are still running the function, we want those sets to be able to change. We want to remove the processables if something failed. We want to add failed elements if they failed, and so on and so forth. So, but at the end of it, we want those values to be immutable. We want to freeze them and prevent any further changes, because that function has completed, it has returned the status, and you do not mess with that status. And then we've got one function which is going to come up later. We've got integrate, which is a static method. And if you give it a bunch of statuses, it will return a frozen summary, essentially, of all executions of every function. So yeah, so I'm basically gonna go into small difference between fail transiently and fail permanently, because we are kind of eager to identify permanent failures. If something is a transient failure and becomes a permanent failure, we remove it from transient to reduce the noise and mark it as failed permanently, right? And we also remove it from processables, obviously, because it's no longer processable. It failed. So yeah, so freeze I have already talked about, and like I said, with integrate, the processables are intersected, because we are only concerned with the narrowest part of elements that have succeeded all the way through, because this kind of circles back to the original definition. We want to return the items that have went all the way through, and the rest is going to be handled by logging pretty much. Transients and permanents are respectively unioned, and then because permanents are more important than transients, we make sure that if anything ended up in both, it's actually a permanent, right? So let's have a look at the process elements function one penultimate time. So first we do the discriminator function, which has basically remained as it was before. And then we, as you can see, we do the integrate, where we run these functions in sequence at first, because every one of those takes process status elements that are still processable as a parameter, processes them, and then returns its own processing status object. So we've got this as a starting point, and once we've got an iterable, there is an obvious next step, which is to make that thing multiprocessing. And basically, if you're not a Python developer, you might be wondering why use multiprocessing.dummy instead of just multiprocessing. And it's basically like dummy uses threads and multiprocessing uses processes, and processes are much heavier. So it's more lightweight to do it that way. But basically, a multiprocessing pool is a pool of essentially threads that are waiting for jobs to do. So what we do is we use the map function of a pool to give it things to do. And it will spin up as however many processes as we want to handle all of that in parallel. So we've basically sped it up, because those functions that were running in sequence can now run at the same time, because because like I said, we don't care about items being partially processed, just as long as they are processable, and just as long as we get a result that we can integrate. So basically, the outcomes, first of all, we've increased the readability by a whole bunch by being able to modularize this properly and have each function have an actual identifiable outcome where it returns the processing objects it worked on. So thanks to the fact that we've got a common architecture in that we're expecting the processing status at the end of the function, we can basically, we've got essentially a plugin architecture for basically free because that was part of our solution anyway. And yeah, as you saw just now, parallelization is much easier to implement. And basically, we've got a major speed boost. At first, but remember, the size of the data can vary. But at first, we've got around 50%. Then it's kind of went like between 30 and 20, and kind of seemed to even out at about 20% increase just by using the multiprocessing pool. But bear in mind that once we've got a structure where we can map those functions across multiple, we can execute multiple functions in parallel. There's nothing stopping us from making those this not just a multiprocessing map, but we could, for example, use SNS plus SQS or RabbitMQ or any queue, whatever, and we could like distribute this however we want, thanks to the fact that this can run in parallel, and thanks to the fact that each component part, each processing status is immutable, and we can guarantee that nothing's gonna, no one function is gonna mess up the execution of another function. Unfortunately, as I cannot show you the diagram itself, I can show you this. So yeah, how are we doing for time? Can we do a Q&A? All right. So, any questions?
So is this inspired from MapReduce? Is it similar to that?
Yeah, that's part of it. Basically, the fact that we can map. And by the way, kind of a curious thing. Let me just. We're kind of doing it in reverse if you look closely, because you're supposed to map it on data, but we're mapping it on functions, right? Which is kind of a quick, but it works because basically the data set is remains the same at the start of it, but basically what changes is the types of functions that do processing. So it's kind of MapReduce, but in sort of in reverse. Okay, so any other questions? All right, so the slide deck is available on, I said I'm going to inflict this on you twice, woźniczak.github.io/kds2021.html. And once you get there, you can click on this thing here and get the PowerPoint as seen on here. So thank you for your time, and